Hello and welcome to this webinar presented by Microtrack MRB. My name is Kai Düffels. I'm from the Application Laboratory of Microtrack in Hahn. My partner today is Jörg Westermann, one of our Microtrack sales managers. Jörg will be answering your questions during the webinar. You can send us your questions anytime via the GoToWebinar control panel, which you should find on the right side of your screen. If we do not manage to reply to all of your questions during this event, we will collect them and come back to you by email in the next couple of days or discuss during the Q&A session after this presentation. This webinar today will be recorded as always, and the webinar recording will be made available to every participant in form of a download link that we are going to send to you later this week. So you will have all the contents for later evaluation provided to you from us. Okay, let's talk about particle analysis, and let's talk about things that can go wrong in particle analysis and how to avoid these mistakes. First of all, we have to know that particle analysis is much more than just taking some powder or some suspension, putting it into an analyzer, pushing a button, and then getting a result. Particle analysis is an entire workflow that involves many different steps, and in all these different steps you can face some problems that can have a negative effect on your result. So the workflow of particle analysis starts with sampling, continues with sample splitting, dispersion of particles, choosing the right technique for your sample, instrument-related issues, and also correct evaluation of the data and of the result. So during my presentation today, I will try to follow a little bit this workflow and start here on the left and then move over to the right, sampling, splitting, dispersion technique, and so on. So this is not a list of mistakes that you can make, from not so bad mistakes to very bad mistakes. I will just try to follow this this process here, and I will give you a couple of examples illustrating how you can improve your particle analysis. So the first item that I would like to start with is sampling. So this is number one on my list, sampling errors. When we try to analyze the particle size distribution of a bulk material, so a powder or a granulate, we are usually facing polydisperse systems. And polydisperse means we have large and small particles in our sample, and we need to quantify the percentage of small particles and large particles. That's what particle size analysis means. So if you have these polydisperse bulk materials, something happens that is called segregation. And segregation means that the particles are separated from each other and sorted by size. And this happens very easily during transport and forwarding, and during deposition. When you transport the particles or the material on a conveyor belt, in the tube, in a container, or on the truck, you usually see that the fine particles are moving to the bottom of the container, in between the big ones, between the voids, in the voids here, and they will collect at the bottom. During deposition, something similar happens, but here the big particles will collect at the in the lower part of the pile and on the outer part of the pile, and in the inner part of this you will have a concentration of smaller particles. So despite inhomogeneous samples and segregation that occurs, a representative analysis sample must be obtained for your analysis. You see very clearly that your result will be very different when you take your sample up here or down here. Here you have the fine particles, here you have the large ones. Okay, so how does it look in the practical work? So maybe you will have to take a sample from a ship, as you see here, or from a truck, or from a train wagon, so a big amount of material. And what you will usually do is you collect several single samples, and from different positions of the amount that you need to sample. And you unite these single samples to a composite sample, which will then be transferred into your laboratory as a lab sample. You can use tools to obtain particles from different levels of your container or from different levels of your bag, like this lens here. So there are various tools available of different size where you can get several single samples from different levels of this material you wish to sample, and that you can unite to a composite sample. If you are lucky, you will have an automated sampling system at your disposal, which might look like the one you see on this image here. This is a conveyor belt, and here is a stream of particles. If I remember it correctly, it was fertilizer pellets. Particles are falling down here, and this little collector box is moving from left to right and then back to the left, collecting samples from all parts of this stream here. So you get, if there is a segregation and the size is different here on the left, on the right, or in the middle, you will get from all parts of this stream your sample. I have prepared a short video that I would like to show you, telling you how this works. I hope this will play well during the webinar. Sometimes it's a bit a problem with the videos, but I think this works quite well. So here you see the particles, you see the collector sliding along. And this is just one example for an automated sampling system. There are hundreds of more, but this guarantees you a representative sample. And theoretically, it's even possible to connect this little box here directly to a particle analyzer that will transfer the particles into your measurement device. Okay, now it plays again, but that is enough. Okay, so we have seen we can make errors during sampling. And this takes us to the second item on my list. And this is not making a sample splitting. And it is very closely related to sampling errors, because when you get your laboratory sample, the quantity provided is often too large for your measurement instrument. Therefore, the sample quantity must be reduced. And when you reduce the sample quantity, you have the same problems and the same challenges as you have during sampling. So with a suitable dividing tool, a representative subsample can be obtained. If you do just random sampling and put that in your analyzer, and you do it several times, then the standard deviation in your result will be high, which also means your repeatability will be bad. This can be improved a little bit by doing something which is called cone and quartering. You make a pile of your bulk material, and then you divide this pile into 4 quarters and take one of them. So you reduce, you get a 25% subsample. You can use splitters like this. This will further reduce the standard deviation and improve repeatability if you measure different subsamples. And the most accurate thing you can do is using a rotating sample divider like this PT100 from Reg here, which will give you the most representative subsamples. To further illustrate this, I'm going to show you now some measurement results, some examples. Here you see different size distributions. What we have analyzed here is kind of standard sand or a reference sand. This sand has been analyzed many times by Sieve and has been characterized very thoroughly. So we can have certified values here where the size distribution should be. This is indicated by these little black and blue asterisks here. So these are the certified target values for this sand. You see also it's a very wide distribution, starting at 100 micron and goes up to 3 or more millimeters. So when we do a sampling of this sand and measure it with a ChemSizer P4 dynamic image analysis system, which by itself is a very accurate measurement device, We measure this sand 4 times with the image analyzer. We get 4 correctly executed measurements, but we get 4 different results because we have done random sampling, no sample splitting. All our 4 subsamples have been different. The consequence of that is that neither of the results will match the target values, and the repeatability is really bad. Things will improve when you use a sample splitter, like one of these devices you see on the lower right of the screen. Again, we have generated 4 subsamples, not by random sampling this time, but by using this splitter. You see we are much closer to the target values, to the certified values, and also the repeatability has improved dramatically. Up here, there's still a little bit of a difference, but here on the fine side of the distribution, we are already quite good. And as I have mentioned before, the best thing that you can do in sample splitting is using a rotational sample splitter where you have a constant feeding on a vibrating tube. And this is distributed in different jars here that are connected to a rotating divider here. Again, we have generated 4 subsamples, this time with the rotating sample divider, measured these 4 subsamples with the ChemSizer device. We see the repeatability is perfect. So these curves are all on top of each other, and the result is also accurate because we match the certified values of this reference sand. Okay, so we have seen how to do it with a powder or a granulate, but in some cases you will have to take a sample from a suspension. Because you want to analyze the liquid sample. And sampling from a suspension is very tricky. It's a real challenge because the big particles, they will settle down to the bottom of your container, as you see here. And bigger particles settle down much faster than fine particles. So there is a dramatic segregation in size, and settling of particles happens faster than you think. And depending on where you withdraw your sample with a pipette, if you do it up here, you will have a very fine result. If you do it down here at the bottom, you will just scoop up all the big particles and your result will be large. So what you have to do when you sample suspensions, the liquid needs to be agitated during sample, also stirred. You can do it on a stirrer plate, or you can use an overhead mixer, which is even better than a stirrer plate. And then you should take your sample with a pipette from the lower third of the beaker, so somewhere here. And then you should take the sample in your pipette and transfer the entire contents of the pipette into the analyzer, because settling of particles also happens within the pipette, and the first drop will contain all the large particles. And if you only add the first drop, your result will be too large. So you have to know a little bit how much you need for your analysis. It takes a little bit of experience, and then transfer the entire contents of the pipette into the analyzer, and that's the best thing that you can do here. But sampling from a suspension is always a bit tricky. So the third item on my list will be related to dispersion of particles, wet and dry dispersion. What do I mean by dispersion? Dispersion means nothing else but separating particles from each other so that they are available for analysis. So what we want to have are single isolated particles, not particles sticking together, not particles forming agglomerates due to liquid films, van der Waals forces, or electrostatic forces. When you are dealing with liquid samples with suspensions, you need to select a suitable dispersion medium for your particles. Dispersion medium is also called dispersant or carrier fluid. Common dispersants are water, alcohol, organic solvents like hexane, heptane, or toluene, and most modern particle analyzers are resistant to those kinds of organic solvents, so they can be used. If you observe poor wetting of the particle surfaces, particles floating on the liquid, this is usually an indication that your dispersion medium is not suitable and you should consider using a different one. Plus, your particles should not dissolve in the dispersion medium. So everything that is water soluble should be measured in alcohol or organic solvent. Particles like to stick together and form agglomerates, and these agglomerates can be broken up in the suspensions by the use of ultrasound. most modern particle analyzers have built-in ultrasonic probes. The effect of ultrasound can be observed here. This is a sample of yellow pigment. The pigment is now it has settled down in form of agglomerates at the bottom of the beaker. I have put in here an ultrasonic probe, and as soon as this probe is starting, you see these agglomerates are broken up, and this turns into a cloudy suspension, and we can measure the single particles. Once the particles have been separated by ultrasound, they sometimes like to re-agglomerate, and this can be prevented by using a suitable surfactant. Surfactants are chemicals that are adsorbed on the particle surfaces and prevent re-agglomeration. Usually these surfactants are in a very low concentration of about 0.1%, and here you see a list of some prevalent surfactants. Sodium phosphate solution is very often used for silicates, for oxides, ceramic samples. Also here, Triton X nonidet, tween 80. These are surfactants that are sometimes used. Sometimes you have to be careful with these surfactants because they chemically they act like dishwasher, so they reduce the surface tension, but they also like to form bubbles, and if you have bubbles in your suspension, they will be measured as particles. Here's an example of the effect of ultrasound on a particle sizing result. We have measured a very fine polishing agent, which has a particle size of around 1 micrometer. We used the Microtrack Sync laser diffraction analyzer. This analyzer has a wet dispersion system that has also a very strong ultrasonic probe built into the circulating system. If you put the powder just into the liquid and measure, you get the red curve, which is still quite coarse. And as soon as you start turning on the ultrasound, the particle size will decrease. After 1 minute, you measure the green curve, after 2 minutes the yellow, and then there's still a little more change with 3 minutes, the blue curve, and after 3 minutes no more changes occurring. So this means you have separated all the particles, your dispersion is good, your result is repeatable. So for this material, you know, you need about 3, maybe 4 minutes of ultrasound treatment to get a good result. So this is dispersion of liquid samples, but maybe you want to measure a powder or a granulate in dry state. This is an example from image analysis. This is the optical design of our ChemSizer X2, and as most devices that measure dry samples, you have here a compressed air that generates an airflow which carries the particles through the measurement zone. And in that measurement zone, the particles are illuminated by light sources, and the particle images are photographed by 2 cameras. This is an example for a camera image. All these particles are evaluated, and from that you calculate your size distribution here. So this is how image analysis works. But my main point here is that this airflow is generated by compressed air, and this pressure can be adjusted. And you can see here, we've measured a milk powder at different dispersion pressures, starting at low pressure of 5 kilopascals and then increasing 30, 80, 150, and 250 kilopascals. In the beginning, at the low pressure, the result is here on the right, the red one. It's very coarse. At 30, it gets finer. 80, it gets finer. And then 150 and 250, there's no more change. So this is the maximum dispersion that we can achieve for this sample here. But you have to be a little bit careful here too, because this compressed air can also have the opposite effect. At very high pressure, particle milling can occur, and this very much depends on the nature of your sample and how fragile your sample is. Here we have measured a lactose powder, and at low pressure, 20, 30, 50, the result is very repeatable, so there's not much happening. And then at higher pressure, then you see it gets gradually finer. And this might be an indication of destruction or milling of particles, which also can happen if your dispersion force is too high. It very much depends on how fragile your sample is. And it has to be decided case by case. It's always a good idea to try to make some trials at different pressure and then think about what is happening and what is the dispersion state you would like to observe. So these topics here, 1, 2, and 3, sampling, sample splitting, and dispersion, are all related to sample preparation. And I will give you a quick summary, or this is a quick summary of the possible sources of error that can happen during sample prep. The overall error is a combination of errors in sample preparation and the measurement uncertainty of the instrument. If you're dealing with small particles and narrow distribution, then you have a small probability of error during sampling and splitting, but a higher probability of error during dispersion. If you have large particles and a wide distribution, then the sampling error and the sample splitting error is usually much more pronounced, more severe than the error that you make in dispersion, because big particles are easier to disperse. Okay, so that was the sample preparation part. We now move forward in our process and come more to instrument and evaluation related topics. And I have called mistake number 4, comparing apples and oranges. This is about different size definitions. So what is particle size? I have prepared an example here where you see on the upper left is a grinding ball, which is a round particle measured with a caliper. It has a diameter of about 15 millimeters. And this is clear and obvious. So no matter how you measure it, how you put it in this caliper, the size is always the same. Now, if you compare this with a Lego brick, which is a non-spherical particle, depending on how you have the orientation here, you get with the caliper very different numbers. Here it's 11.5, here it's 15, almost 16, and here it's 23. So if you have non-spherical particles, you have to decide what dimension you wish to measure. But it also depends on the capability of your measurement instrument. You can have any orientation with the caliper here, but if you put these particles on a sieve, you see that this is a 16 millimeter sieve and both particles fit through the holes. And on a 14 millimeter sieves, both particles will be retained. So for sieving, these two particles have the same size. They have the same equivalent diameter. They are between 14 and 16. We cannot be more accurate because I did not have any sieve in between. So with caliper, you get different size definitions, different measurements, and with sieve, you get the equivalent diameter, and these two are the same in size. But I think not very many of our participants will use a caliper for size measurement. So let's go to more practical, relevant examples. Again, if you do image analysis with a cam sizer P4, cam sizer X2, in image analysis, you can select what your size definition should be. So this black structure here is a particle that has been photographed by the image analyzer, and you could measure the width of the particle, you could measure the length, or you could measure the diameter of a circle that has the same area as the particle image. And depending on how you define particle size, width, length, or equal area diameter, you get 3 different distributions. This is the width distribution, this is the length distribution, this is the equal area distribution. And you will choose the one that is most relevant for your application. When you do laser diffraction is just evaluating a scattering pattern that is generated by all particles simultaneously. This would be the scattering pattern from 10 micrometer particles, and this would be the scattering pattern from 1 micrometer particles. You see the pattern looks different, and this can be evaluated by the software, and this gives you the particle size. But all these scattering or diffraction data are related to a spherical model particles. It is treated as if this pattern would be generated by round particles. Now, if you compare image analysis with sieving and laser diffraction, this is what you usually find. Again, here we have the 3 size definitions from image analysis: width, length, and equal area. The black asterisks here represent the data points from sieving. They match very well with the width measurement because sieving has a tendency to measure particle width. And laser diffraction, because it relates all scattering data to spherical particles, it's much closer to the to this equivalent circle diameter to the blue curve, but it also approaches the blue curve of the length, because the length is treated as if the length of the particle would be just a big sphere. So with image analysis, you can somehow simulate both sieving and laser diffraction. So it has more information content, but laser diffraction is very hard to correlate to sieve analysis. And if you do that, it's really, you will have a hard time. We could make a whole webinar on comparing different sizing techniques, but this is just a quick glance that you know that different techniques use different size definitions, and so this also affects your result. Okay, number 5, inappropriate sample quantity. Let's look at an example. Here we have 2 results of particle sizing of the same sample. The red curve is a cam sizer measurement, so dynamic image analysis. And the black curve with these data points here is the corresponding sieve result. We have seen on one of our previous slides that we can get a very good correlation of image analysis with sieving, but this is not the case here. So why is it? This is not what we would expect. So we were curious what happened here, and we have taken a closer look at these sieve data that had been provided to us from another lab. And this is the data table, about 8% smaller than 250 microns. And these are the other fractions. And we can see here, this does not add up to 100% as it should. So there is some mistake in there, obviously. So we took the sample and sieved again in our lab. And you see here, these numbers are dramatically different. Here we have more than 40% smaller than 250, and all the other numbers are different too. And if you add them all together, you get to 100%. So let's plot the result from laboratory 2 into this diagram. And this is how it looks. And now we get a very good correlation to the cam sizer. So what happened here in laboratory 1? These people have been lazy. They have done something that you can do, or that some people do if they don't want to do math. They always take 100 gram of sample in sieving, because then gram equals percent. But in this case, 100 grams has been way too much. So the sieve has been overloaded. It will look something like this. This is an example for an overloaded sieve. You see all these small particles sitting here in the holes, and will not, they are stuck in here, and this prevents small particles that are still here on the sieve to pass and to go into the finer fraction. So if you see this, that the sieving is much larger than the image analysis, it's usually an indication for overloaded sieves. So what do? Use less. Yeah? So there are some standards, some recommendations of how much sample you can put on a sieve with a given aperture. I will include this in the download package, maybe, so the reference, so that you can look it up. Okay, so we have seen using too much or too little sample quantity can deteriorate your result, can have a negative effect on your result. In laser diffraction, too much sample will lead to multiple scattering, which will affect your result. If you do not have enough, you have a bad signal to noise ratio, also makes your result less accurate. But here, the measurement software that you have will usually give the operator a clear indication for the optimum sample concentration range. So this mistake does not happen very often. In image analysis, you can not use too much sample, but it will increase your measurement time. You just have to make sure that your images are not too full, because then particles will be touching each other on the image and will be measured too large. But if this coverage on the image is okay, you can measure as much as you want. It will improve your repeatability because your particle count is higher. It just depends on how long you wish to measure. If you use not enough sample, then you will see that your repeatability is decreasing, because your overall detection number is also going down. How much you need in image analysis strongly depends on the size and the width of the distribution. With wide distributions, you usually need more sample. But the most common error with sample quantity is overloading sieves. Okay. Brings us to item number 6, underestimating tolerances. And again, I will give you an example from sieve analysis, because a test sieve is also a measuring device. These test sieves are produced by our sister company Reg in large numbers, tens of thousands of sieves every year. And every sieve that leaves our factory will be inspected prior to shipment, so that it complies with the relevant standards, which in this case is the ISO 3310-1. And in this standard, you find the allowed tolerance for the real aperture of a sieve with a given size. And you can get, with every sieve, you can get a calibration certificate where you can see the real aperture size of your sieve. These sieves are inspected with an optical method. It's like a microscope where we inspect a given number of holes. This is an example for a calibration certificate of a 400 millimeter sieve, 400 micrometer sieve. And you can see here, these two numbers indicate the tolerance for the mean real aperture size. So you have a tolerance for the mean aperture of plus minus 13.3 micron. Yeah? And you also have a tolerance for the maximum allowed opening, which would be almost 470. So if you have a 469.8 micrometer hole on that sieve, it still complies, it's still okay, yeah, as long as the mean is within this range. For this 400 micrometer sieve, we have measured more than 2,000 openings in each directions. Every wire fabric has 2 directions, and they are measured separately. And you can see here we have we are very close to the nominal values. In the other direction, we are a bit larger, and the maximum holes, the maximum aperture size that was found was here 422 and 429, almost 430. Here you can see the distribution of the aperture. The consequence of this is that you see here we have some holes that are larger than 400 micrometers, and this will allow bigger particles bigger than 400 to pass this sieve. They will not be retained. If you sieve long enough, they will find the big holes. Let's see what's the consequence. Again, we have this chart here where we compare image analysis. This is the red curve with sieve data, which are the black asterisks here. Okay, we've seen similar things before. And this time, the correlation is really good, but there's a very slight offset. The particles that we have measured here was expandable polystyrene beads. These are very round particles. This is an image from the ChemSizer. So we would not expect much difference between ChemSizer and sieving, because round particles, so we don't have the problem of different size definitions, right? If you look at this data point very closely, you see that there is a difference in 5% in amount, which sounds much. 5% is a lot, but the difference in size is only 10 micrometers. And as we have seen on the previous slide, for a 400 or 450 micrometer sieve, 10% is very well within the range of the tolerance. And this explains this little offset here. Not only when you compare ChemSizer with sieving, but also if you compare different sieve stacks, maybe one of your sieves is at the lower end of the tolerance and the other is on the upper side of the tolerance, you get different results that are somewhere in that range of several percent. And this is something that people experience when they, for example, buy new sieves. They get different results because the new sieves are maybe a bit closer to the nominal values, are a bit different than the ones they have used. Plus, your real aperture and your sieve tolerance can change over time. This depends on how much you brush your sieve and how you treat it. So this is an example for a worn out old sieve, and if you really have this these old test sieves, you see the holes are just not very reliable, the apertures. Okay, so treat your sieves well. So this was underestimating tolerances. The next point will be overestimating sensitivity. And I'm going to show you an example from laser diffraction. What we have done here is we have taken a sample of glass beads, and these glass beads have been entirely smaller than 75 micrometers. This can be produced very easily by sieving. You just take a 75 micrometer sieve, and everything that passes is your sample here. And then we have added about 1 volume% of glass beads that are larger than 125 micron. We call that oversize. Oversize is just means a small percentage of particles that are much bigger than the rest. When we take this sample with the oversize and we analyze it with laser diffraction only, this was also the sync analyzer that I've shown you before. You see we measure the glass beads smaller than 75, very accurately, but the oversize does not appear. This is because laser diffraction is evaluating a diffraction pattern that is generated by all particles simultaneously, and the contribution from the large particles is just not big enough to generate enough signal on the relevant detectors to be represented in the result. Now, the sync analyzer has a special feature. It has a built-in camera, so you can do both. You can do image analysis and laser diffraction, and you can blend the image analysis result into the diffraction result and make a kind of a combined analysis. And when you do that here, you not only get images of particles, these are the small glass beads and these are the large glass beads, you also get a much higher sensitivity for the oversize. So here you see these particles are represented in the result here in the graph. So here's the arrow. It's a very small bar here, but it is there. And this can be found in the results. So by blending the imaging results into the diffraction results, we increase the sensitivity. Very often you will see measurement reports from pure laser diffraction analyzers that put out percentiles at 99%, D99 or D99.9. So the percentage at 99.9%, or even a D100 values. As you see here, these numbers are a little bit doubtful because the sensitivity of the unit might not be there, of the method might not be there. Okay. Also, a D100 value is not defined. If you look here, D180 is D100, 125, 290 is also D100, so it's a meaningless number. And now discussing D99.9 is somehow a futile discussion. Okay. So check your device sensitivity and know how reliable the oversize can be detected. Okay, number 8 is a topic related to evaluation and to how particle distributions are represented in a graph. I have shown you during the previous examples almost cumulative distributions, so curves like this blue one here. But for some reason, many people like to look at density distributions. That would be this red curve here. And the density distribution is the first derivative of the cumulative distribution. This means we measure the slope. Where the slope is very, very steep, you have a maximum. And where the slope is flat, you get a minimum. So we calculate the slope of the cumulative distribution and get to a density distribution. The unit here is percentage per length, percent divided by length. Okay, and this is the real density distribution. In very many cases, your sizing result that you get from your analyzer or from anywhere is reported in a data table. And what people do is they take this data table and make a histogram. Here we have the histogram of this size distribution with linear bins. It's a linear x-axis and we have linear bins. You see, this is very close to the density distribution. And if I would make these bins more narrow and if I had an analyzer that is capable of doing this, we could get even closer. But in very many cases, you have you get a result that is not in linear bins, but that is in logarithmic bins. And what I'm now going to do is I just changed the bin size from linear to logarithmic and plot it in this graph and see what happens. So here, these classes, these fractions are more narrow. So there's not so many particles here. The percentage is going down. Here we have wider classes and they go up. So this looks like the whole distribution is shifted to the right. And what people do is they take the data table, they plot it in Excel, they get a chart like this. And what you can do very easily with Excel is making just a kind of plot like this that just connects here these bars. And then people think they have a density distribution, but they don't. This is not correct. The red one is the real density distribution, not the black one. So this is not just a party trick, but it causes some confusion in real life. We had one case where the same sample has been measured with 4 different laser diffraction analyzers from different manufacturers, and all these results were gathered, and then somebody made what we've seen here. Plot it in Excel and just make these nice line charts. And what they found is, oh, they all look different. And the conclusion was, oh, laser diffraction is not a very reliable method because every analyzer gives a different result. But if you take the actual data table from which these wrong density distributions have been generated, and you plot it as a cumulative distribution, then you see that the results are not so different. So the D50, D90, D10, they are very close together. There are some differences in the percentage of finds and oversize that can be related due to sampling or sample preparation or ultrasound, but the overall agreement between these 4 laser diffraction analyzers has been quite good. Okay, number 9. Number, volume, intensity-based distribution. So what do I mean by this? Your sizing result will always be reported in some kind of percentage values. And percentage can be volume percent, mass percent, number percent, or something else. Look at this example here. We have a size distribution with fine particles, medium-sized particles, and large particles, 5, 10, 15, and 40 millimeters. Now, by weight, they are all the same, all 190 grams. So each and every fraction, each size has 25% of the entire amount. But if we count the particles, we find that there are much more small particles, almost 500, but we have only one of the very big particles. If you calculate your percentage from this as a number-based distribution, you see 85.5% are small particles and only 0.2% are large particles. So this might cause some confusion. There are some techniques, some analyzers that will generate number-based distribution. For example, the caliper that we have seen, everything you do with hand measurement is a number-based distribution. Image analysis gives you number-based distribution, especially microscopy or static image analysis, like the ChemSizer M1 here, and all devices that do particle counting, like for example the Coulter counter or some dust monitor that you use to observe the cleanliness of a clean room or something like that. There are also methods that give you volume or mass-based distribution. Sieving gives you mass-based distribution because sieving is weighing. Laser diffraction gives you volume-based distribution. And dynamic image analysis data from the ChemSizer devices, ChemSizer P4, ChemSizer X2, will also usually be reported as a volume-based distribution, because here we can do a very good conversion from number to volume. We measure width and length of the particles. This gives us a very accurate volume model, so the conversion from number to volume works very well. You can also convert the volume-based laser diffraction results to number-based, but this will only be a very simple sphere model and will have some inaccuracies. Okay, so volume and mass can be converted into each other, and it works especially well if you have a good volume model like in dynamic image analysis. We treat volume and mass usually as equivalent, and you can do this as long as the density of your particles does not change with time. So Here, these balls have all the same density, all the same material. If this was metal and this was plastic, then volume and mass would no longer be equivalent. If you do dynamic light scattering, it's a bit of a special case. Here you get intensity-based distribution, which means the different sizes in your result will be weighted by their contribution to the overall scattering intensity. And this gives a bit more emphasis to large particles because large particles scatter much more light than small particles. But here also, this intensity-based distribution can be converted to a volume-based distribution. You just have to make sure when you compare dynamic light scattering results that you have the same distribution base. So how can this confusion be avoided? By paying attention. So my final point, would be not using SOPs. So everything that we have discussed here before should be converted somehow in a standard operating procedure that makes sure that we always do the same thing. Especially in quality control, it is important that all steps of the analysis and the sample preparation are performed in the same way. By doing this, you can get consistently reliable results. When comparing results from different locations, the use of a standard operating procedure can help to avoid errors. The standard operating procedure is not only the settings of the instrument and the evaluation, but it really comprises the entire process, the entire workflow that we have seen on the first slide that I have shown you. Every modern particle analyzer, laser diffraction, image analyzer, all these settings that you use for sample feeding, everything that is instrument related is saved in the file. So just by calling up this SOP here, you make sure that your instrument settings are always the same. But there's more to a good SOP than just instrument settings. Okay, so these were 10 possible mistakes, sources of error that can happen in particle sizing. I hope they don't happen to you in the future. Maybe I could give you some help in improving your work. This brings me to the end of my presentation. I will now ask my colleague Jörg, how is the response from the audience? You can unmute yourself and talk to us.
Yeah. Hello, everybody. Yeah, the response from the audience is great. I received a lot of questions. Kai, I have 3 questions for you, which we maybe can discuss quickly. The first one is, can you comment on the use of external ultrasonic probes versus the ultrasonic probe that is included in the analyzer for the wet dispersion?
Yeah, okay. I would say from my experience, in 90% of the cases, the built-in ultrasonic probe is good enough. There are some materials that are hard to disperse where the use of an external ultrasonic probe can be advantageous. This has always to be decided case by case. I know it's a bad excuse. We always say that in particle analysis, it's all sample dependent, but it's also true. I would say 90% would be okay to use the internal ultrasound. The only way to find out is to try the external probe if you have the suspicion that the dispersion might not be good enough. When you do the external preparation, please note that you introduce also a sampling error. So if you have large particles, preparing it in a beaker and then sampling from a beaker is always an additional source of error because you might have sedimentation in the beaker if you have large particles. So I like very much the idea of putting powder directly into the analyzer and then applying ultrasound.
Okay, thank you, Kai. Second question, I would like to ask, what is a proper way of cleaning and treatment of the sieves? So after the analysis, how should the sieves be prepared for the next analysis?
Okay, so I see where this question is heading to. So you want to avoid this one here, yeah. You can use a soft brush for your sieves. for everything that is, let's say, larger than 500 micron. For everything else, we strongly recommend an ultrasonic bath, where you put in your sieves for 3 minutes, and this ultrasound will remove the particles from your sieve.
Yeah, we are getting many more questions in the meantime, but I would say I just ask one more before we stop this session, and thank you for all the many nice questions. We will come back to you later with the answers to your questions one-on-one. Yeah. So one last question. Does the internal ultrasound probe produce bubbles?
Actually, no. Bubbles are produced if you have a water that has not properly been degassed, that comes fresh from a pressurized tap. Ultrasound can actually prevent bubbles, can remove bubbles from your solution. It produces bubbles in alcohol, but these disappear usually by stirring. Most common source of bubbles is if you use too much surfactant or are not careful with the surfactant.
Okay, then thank you very much, Kai.
Thank you, Jörg, for handling the Q&A session. Thanks to all the participants that have joined us today. I hope you enjoyed it, and I hope you will come back to see one of our future webinars. Please remember that the download package will be provided to you by email in the next couple of days. I hope I will do it tomorrow, otherwise later this week. Thank you for your attention. Thank you for your time. Bye-bye. Take care.